exponential and logarithmic equations. All right, to start us off, I would like to do a bit of a warm-up. Just a refresher from last time. So if I was to give you 2 times log base 8 of x plus log base 8 of x plus 2, what would this be? Take a second and try it out. All right, so both of these logarithms have the same base. So we know that we can combine them using the product rule, right? Product rule says addition on the outside becomes multiplication on the inside. But before we can use the product rule, we have to use the power rule to bring this coefficient in. We can't combine until we have all coefficients of 1. So let's bring this 2 to the inside. That if we brought that to the inside, we would get x squared. And then that x squared would be multiplied by this x plus 2. So we have x squared times x plus 2 on the inside here. Great. Okay, so how can we use that to solve logarithmic equations? Let's start off by looking at sort of some steps to do so. So solving logarithmic equations. So for the most part, we want to start off here by isolating one logarithm. It is important that we have one logarithm, and you'll see why in just a minute. In order to make sure that we have one logarithm, you may need to combine using laws of logarithms. So, like the laws that we used here to combine. Next step is to rewrite in exponential form. Once we've rewritten, all we have to do is solve. One little note here, though, to add at the end is that we need to check. And the reason we need to check is that we cannot take the log of a negative number or 0. So why is that? Well, remember, if we look at the graph of a logarithm, in general, it has this shape, right? We have that vertical asymptote at x equals 0, and we don't have any function over here. The domain is from 0 to infinity, with 0 not included. So these are the only numbers that we can take the logarithm of. So for example, log base 2 of negative 3 is undefined. Great. Another quick example is if I was to take the ln of x plus 3, well, x plus, let's say 5. When is this defined? Well, if we know that the stuff on the inside needs to be greater than 0, let's set the stuff on the inside greater than 0. This means that x needs to be greater than negative 5. Let's look at a few examples of this. All right, let's start with something simple. Let's say we've got log base 2 of x plus 1 equals 3. So my first step here is that we want to isolate the logarithm, but that's already done for us. This log is on its own on one side of the equal sign. It has no coefficients. It has nothing added to it. It's isolated. So we can go ahead and rewrite it in exponential form. Exponential form, we have base to base, so 2. The exponent got exiled, so 3 is our exponent, is equal to x plus 1. So we want to solve for x. X equals 2 to the third plus 1. 2 to the third is 8, plus 1 is 9. That's my answer. Let's do one that's a little bit more tricky. Let's say we were given log of x plus 3 plus log of x equals 1. Okay, so now we don't have one single logarithm isolated, so we do need to combine here. We need to use product rule to combine these two logarithms. So we end up with log, it's addition on the outside, so it becomes multiplication on the inside. So we have x plus 3 in parentheses times x equals 1. We can choose to simplify now, or we can simplify later. I'm going to simplify later. So now that we have this logarithm isolated, let's go ahead and rewrite it as an exponential. So what is my base here? It's not listed, so that means that it's 10, right? Common log. My exponent is 1. And my old input is now my output. So x plus 3 times x. From here we need to simplify so we can solve for x. So we have 10 equals x times x plus 3 times x. How can I solve this? It's a quadratic. So in order to solve for x, I have to bring everything to one side and factor. So let's bring that 10 over. We get 0 equals x squared plus 3x minus 10. How can I factor that? X plus 5 and x minus 2. All right. So that means that I've got x equals negative 5 and x equals 2. Awesome, so we've solved. Are we done? We are not quite done yet, right? Remember, we need to check and make sure that these numbers will go into these original logarithms and not cause any problems with domain. So does -5 work? Can I plug in -5 for x and get all positive numbers inside these logarithms? It does not, right? If I plug in -5 here, I get -5 plus 3, which is log of -2, right? This gives me log of -2 plus log of -5. Both of these are undefined. So this does not work for us. If I plug in 2, I get log of 5 plus log of 2. This works because we get log of 5 and log of 2, which are both positive numbers. We can take the logarithm of a positive. So this is our answer, x equals 2. Let's try another. So let's say we've got ln of 5x minus 4 equals ln of x. ln of 5x minus 4 equals ln of x. So we've got to isolate one logarithm. We've got 2 here. How are we going to be able to do that? Well, we've got to bring them all over to one side in order for us to isolate them. So let's go ahead and do that. We've subtracted ln of x from both sides, so this side is 0 now. Subtraction of logarithms on the outside does what on the inside? We can combine them, but what happens? The term that was subtracted moves into the denominator. So we have x underneath here. Okay, so now that we have this logarithm isolated, let's go ahead and switch to exponential form. So our base is what here? The base of ln is e. So we have e raised to the 0 is equal to 5x minus 4 over x. Over x. What does e to the 0 become? What does anything to the 0 become? Just becomes 1. Over x. All right, so how are we going to solve for x here? This looks kind of ugly. We can just multiply both sides by x to get this x out of the denominator. And then from here, it's just a simple algebraic equation. So let's bring this x to this side. And let's bring this 4 to this side. We divide by 4 on each side. X equals 1. Let's check and make sure that this works. If I plug in 1 up here, I get 5 times 1 minus 4. 5 times 1 is 5. 5 minus 4 is 1. So we have ln of 1 equals ln of 1. Just plugging it straight in. So not only did we check that it's positive, not only did we check that that makes our input positive, but it's also pretty clear that this is the correct answer. I do want to talk really quick about how we could have solved this in a bit of a quicker way using this method of like bases. So remember, if we have b to the log base b of x, what is this equal to from our laws from last time? It's okay if you don't remember. But this is equal to x. And that's because we're composing this function with its inverse. So we get out what we put in, x. How can we use this here? Well, so both of these sides have the same logarithm. Nothing else, no coefficients, nothing added or subtracted to them. And what we can do is we can take both sides and raise e to these exponents. E to the ln of 5x minus 4 is equal to e to the ln of x. And this is true because these are the same. These are equal, so we know that these will be equal. But what does this rule tell us about this? Well, it says that since we're taking e of ln of this input, these guys kind of cancel each other out, right? Kind of like this is canceling itself out here, right? And we're just left with x. So here, we're taking e of ln of this stuff. Means we're just left with 5x minus 4. Same thing on this side, we're just left with x. So then we can solve from here, just in the same way that we did over here, and we end up getting x equals 1. Okay, let's say we've got 2 times log base 2 of x equals log base 2 of x minus 1 plus 2. All right, so we need to combine these logarithms so we can isolate them on their own. Because we have this 2, we can't use that same shortcut that we used last time. So let's go ahead and bring this guy over to the other side. So we have 2 log base 2 of x minus log base 2 of x minus 1 is equal to 2. Can we combine these guys? We can, but we have to make sure that we get rid of this coefficient first by using the power rule to bring it inside. So log base 2 of x squared minus log base 2 of x minus 1. And now that we have them with coefficients of 1, we can combine these using the quotient rule. Quotient rule says again that because this guy is negative, this is going to go in the denominator. So we have log base 2 of x squared divided by x minus 1 is equal to 2. All right, now we have one logarithm isolated on its own, so we can go ahead and write it in exponential form. Base to base, our new base becomes 2 from this base. Our exponent is 2. And our new output is our old input, so we have x squared over x minus 1. Great. Let's go ahead and simplify. So 2 to the 2 is 4. In order to simplify something like this, we want to get x out of the denominator as soon as we can. So let's do what we did last time and multiply both sides by x minus 1. So we end up with 4 times x minus 1 equals x squared. Again, we have a quadratic, which means that in order to solve for x, we have to bring all of the terms over to one side. So let's go ahead and begin simplifying here. So let's distribute 4 to both of these terms. So we have 4x minus 4 equals x squared. And let's bring this all over to this right side. So we have 0 equals x squared minus 4x plus 4. Okay, and how can we factor this? What multiplies up to positive 4 and adds up to negative 4? Negative 2 and negative 2. All right, so what does this give us? It gives us x equals 2. Let's go ahead and check that, make sure that it works out up here. If I plug in 2 here, do we get a positive on the inside? Yep. If I plug in 2 here, do we get a positive on the inside? 2 minus 1 is still positive 1, so this is good. Okay, now that we've looked at a little bit on how to solve logarithmic equations, let's talk about solving exponential equations. So some steps for this. Are very similar to the steps for solving logarithmic equations. We want to isolate the exponential term. Once we do that, we can rewrite in log form. And then we just have to solve. All right, so example, let's say we've got 2x plus 1 equals 16. Again, we're trying to solve for x here. All right, well, we've already got an isolated exponential, so we can go ahead and write it in log form. So let's switch to log form. Base to base, we end up with log base 2. Our output becomes our input. That's x plus 1. Now that we're here, we know how to simplify something like this, right? What can we raise 2 to get 16? Two times 2 times 2 times 2. 4, right? Is equal to x plus 1. So the answer is 3. Now, there's a similar shortcut to solving something exactly like this, and it has to do with the numbers that we started with. So I want to point that out really quickly. This again is called the method of like bases. So we're starting with 2x plus 1, We also know that we have 16. 16, if you can remember, is 2 to the 4th. Similarly to the problem before that we were talking about, where we had the same logarithm, now we have the same base here. Because we have the same base, we know that these exponents have to be equal. So we know that x plus 1 is equal to 4. And x equals 3. So this is another sort of shortcut for this problem. Let's look at some more examples. All right, let's say we've got 2x plus 4 plus 5 is equal to 10. Remember, we have to isolate this exponential before we can do anything. So let's bring this 5 over. Can we use the method of like bases? We can't. We can't use the method of like bases here because we can't write 5 as 2 to something else. So we have to use our original method. So we've isolated. So now we can rewrite in log form. We've got base to base, so our base is 2. Our output was 5, so now our input is 5. And now my output is x plus 4. We solve for x. We get log base 2 of 5 minus 4. And that's the answer. This is what's called an exact answer, because if we were to compute this log base 2 of 5 and find that decimal and then round it in any way that would let us write it down on a sheet of paper, maybe we rounded it to 2 decimals or 4 decimals, or even if we rounded it to like 27 or even 100 decimals, we would still be cutting off a ton of information. Because this is a decimal that goes on for essentially forever. So it's only exact, we only include all of the information if we leave it as a logarithm. So that's what we have here. This is called exact. Okay, let's look at another. All right. So we've got a little bit of simplifying to do before we can swap to logarithm form. So we've got to bring this 5 over. This becomes 12. We divide by 2. Now this exponential is isolated, and we can swap to log form. The inverse of e to the x is ln. Base to base, we have log base e, or ln, of our old output was 6, so our new input is 6. And our old exponent was 2x plus 3, so that exponent gets exiled. So we've got ln of 6 equals 2x plus 3. We can subtract that 3 over. And then the last thing to solve for x is just to divide by 2. And that is our exact answer. Okay, so there are a couple of problems that I would like for y'all to try in the lab manual. The lab manual does a nice job of sort of guiding you through these steps on this page, and I think it'll be very beneficial for you to see what's going on. So go ahead and take a second and work on that before continuing on in this video. All right, the last thing we are going to talk about in this video today is a very specific problem that we work with when solving exponential functions, where we have two different bases, and we want to solve for x with two different bases. So something like this. So the way I'm going to work this out is I'm going to do the work on the left side of the paper, and I'm going to write down some steps on the right side of the paper. So steps, and they'll follow along directly. What can we do here? How can we bring something down from the exponent? We can use power rule. If we take the log of something like this, our exponent can come to the front if we use the power rule. So let's take the log of both sides. Should we take log base 4 or log base 3? It actually doesn't matter. Neither one is going to help us any more than the other. I actually choose to use neither. I use natural log, log base e, and the reason for that is nothing other than that it's the shortest one to write. We are going to have to write it a bunch of times, so I'm just choosing the one that takes the least amount of time to write. So I'm going to take ln of 4 to the 2x plus 3 and ln of 3 to the x plus 1. So this is step 1. Take ln of both sides. Okay, again, why did we take the ln of both sides? We did it so we could use power rule to bring these guys down from the exponent. So 2, use power rule to bring exponents to the front. So we're using power rule to bring exponents to the front. So 2x plus 3 times ln of 4 is equal to x plus 1 times ln of 3. All right, so we want to get these x's separated from all this stuff. So let's get it separated from the rest of the stuff that it's added to. So we can do that by distributing and creating separate terms on this side and here. So 3 distribute, that's it, distribute. So we are distributing ln of 4 to 2x, so 2x ln of 4 plus 3 ln of 4 equals x ln of 3 plus 1 ln of 3, or just ln of 3. Okay, so now these x terms are sort of free to move to whatever side they need to be on. So let's bring all of the x terms to one side. So this guy's good to stay where he is. We want to move x ln of 3 over here. And while we're moving these x terms to one side, that means we want to move terms with no x to the other side. So let's go ahead and take this 3 ln of 4 and bring him over here. We know this ln of 3 is still here from before. So ln of 3 has stayed, and then we're bringing 3 ln of 4 over. Okay, so now we've got to get this x free from all this stuff that's over here now. What are we going to do to get the x pulled away from these things? Both of these terms have an x in common. What do we normally do when we have something in common with two terms? We factor it out. Step 5, we are factoring out x. So x, what's left over for this first term? 2 ln of 4. We pulled out x from right here. What's left over? Just minus ln of 3 is equal to this stuff. We don't need to do anything to the other side. Now, I've got x times something is equal to something else. What do we usually do when we have that situation? If I have 2x equals 4, what do I do to solve for x? I divide. So here I've got x equals ln of 3 minus 3 ln of 4 divided by 2 ln of 4 minus ln of 3. And this is my answer. I know it's sort of a doozy of a problem, but hopefully with these steps, it'll be a little bit easier. All right, let's try another example really quickly just to make sure we see exactly what's going on here. So, example, let's say we're given 7 to the x equals 2 to the x plus 1. All right, my first step from before was to take the natural log of both sides. So let's go ahead and do that. ln of 7x equals ln of 2x plus 1. We took the natural log so that we could bring these exponents out front. So let's bring x down using the power rule. So we have x times ln of 7 equals, we're gonna take this exponent down as well. So we've got x plus 1 times ln of 2. Great. Now we can distribute. We only have to do it on this side this time, which is kind of nice. So ln distributes to x, so we have x ln of 2 plus 1, so we have 1 times ln of 2, or just ln of 2. Let's bring both terms with x to one side. So we're bringing this x ln of 2. This is minus, I sort of messed up a little bit. So we've got x ln of 7 minus x ln of 2 equals ln of 2. We can factor out x from both terms here. and divide. And that's our answer. Okay, that's all I have for us today. Thanks, guys.